Hello all, welcome to the AI driven perception learning and mapping for drones course. This is the 12th lecture, which is again foundation of convolutional neural network. We focus the outline of the lecture is we focus a quick recap on weight initialization and its effect while we are training the model. We also look at the covariant shift effect which would be there while we are continuously training different layers. We would look at the effects of normalization, why it should be used and how it helps us to address the scale mismatch. Okay. Finally, we will also take a closer look into the domain of dependence or different kind of features which are learned by these convolutional backbones. So, what does the shallow layer learn, what does the deeper layer learn, and finally what are the important backbones which have been there for a long time, and a quick review of certain new backbones in literature. Okay. So, this is something we saw in the previous lecture, which is we had a particular single layer perceptron and we had the loss L. We saw how using chain rule we can write dou L by dou Wi as dou L by dou y by dou z times input. We can observe from here that the gradients depend on the activation functions and on the inputs. Now, the sign of the gradient actually depends on the inputs. So, if the inputs is already always positive, then the gradients could actually follow a zigzag path, not a straight path. Now, this would essentially lead to a slower convergence or inefficient learning, since the optimal path would be a straight path. However, since only zigzag movement is allowed due to the updates in the weights, it would essentially have an issue with the learning. We also went through an example where we saw that there could be scenarios where the optimal weight update requires W1 to increase and W2 to decrease. So, essentially one weight should increase in magnitude, so move in a different direction, and weight 2 W2 should maybe decrease, and in that example we observe that that may not always be possible if this constraint is there, right. And if the inputs are always positives, we may not always be able to get the most optimal learning path, since you cannot do both, which is increase and decrease of different weights in the perceptron model simultaneously. This would focus more on a zigzag path in the loss function. We also saw some effects of the activation function. We saw that there are activations like sigmoid which are not zero centered and which may cause certain effects on the gradients. We saw how it would maybe cause something known as vanishing gradient problem, where the gradients or the derivative of the activation function is so less in magnitude that it would essentially affect the delta W, right. So, it would essentially affect the dou y by dou z part of the chain rule, which would essentially decrease the magnitude of delta W. Right. This essentially would also be an issue and would cause slower trainings, especially in deeper models, because as we keep on having deeper models, this chain rule kind of becomes more and more longer, and hence the effects of different types of weights also has an influence. So, if we have sigmoid in all these weights, then the multiplication of all these small numbers, which are essentially the derivative of the sigmoid activation functions, will be a very small number. So, the update of delta W towards the shallower part of the backbone would be very minute, and hence activation functions should also be chosen in such a way that they do not negatively influence the learning. Okay. Now, let us take a different look into the scale mismatch problem. So, we could have scale mismatch because let us assume that the input features have different scales. So, one feature is at 0, 1 and one feature is in the range of 10,000. If we have something like this, then we can observe that the gradient landscape becomes elongated and ill conditioned. Essentially, we even saw this in our tutorials, that when we used to look at the contours of, let's say, W1, W2, they used to be a very simple kind of a concentric kind of a figure. However, if these scales are not in order, if they are wildly varying as observed in this condition, in this graph where W1 is large scale features and W2 is small, we can see that these are now much more elongated, and hence we define this term, this to look like an ill conditional graph. Now if the input data is not normalized, then we have an uneven gradient flow. Why is that? Now in the weight update during backpropagation, we came across this particular formula when we were trying to use the chain rule on multi-layer perceptron. We saw that the weight correction, which is given as delta W, is essentially learning rate times the local gradient times the input signal to the neuron. Now if the input signal has a scale issue, so if the input signal has a scale issue, then this delta W would get the update not in the right range, and let's come back to what do I mean, bigger update than required. Similarly, even the local gradients have a similar influence to play. If we have some weights, for example, if I have W1 to be very high and W2 is essentially the delta W2, right? Now, okay, let's not keep it delta W2, let's keep it delta W2 dash, which is essentially we have this in the deeper part of the network, and we have delta W dash which is in the lower part of the network. So a very quick figure would be this. So I have delta W1, W2 in the deeper part of the network, and I have delta W2 dash which is in the shallower part. So I know that the gradient flow would be in this manner. Now if that is the case, and if the scale of W1 is too high, then the delta W2 dash, which is given by this equation, would also not respect the scale, right? The local gradient influence by W1 would be very high, and hence there is a scale mismatch. Now the scale mismatch is there even while training the model, right? So even in the learning algorithm, this does have an influence. Now let's take a closer look. Let's assume I have W2 and I have W1, right, and I have an error E. Now we have seen this plot before. This is very similar plot. We are well aware of this plot. We have an error function E. We can start from a randomly initialized point, and using gradient descent, essentially we would want to attain a local minimum value. However, if there is a scale mismatch, as we discussed in the previous slide, then if my W1 is too high compared to W2, since there is a scale mismatch, right, the updates would not be a proportional update. So although I would have wanted W2 to reduce, I can see that due to the influence of W1 it increased by a long margin, and vice versa, right. So hence we have again a zigzag kind of a learning where this is not optimal. So the feature scales actually stretch the error surface. The projected contours shows us that this is an ill conditional curve, and hence this is not the most optimal way of learning. Now this particular part is left as a future read. The Hessian of an optimization problem, if it is close to an identity function, it means that it is easier to find the solution. Please read this particular paper by Jan LeCun. We will discuss this in detail in the next lecture. Okay. Now we can write the loss del L by del W is X, right. Now if we make the expectation of X to be 0, when I say expectation, it means the average of that particular input is 0. So essentially sometimes the input is positive, sometimes the input is negative. If that happens, then del dou L by dou W has the flexibility to change sign regardless of the error or the activation function. And if that happens, then that's a better way to learn, because your gradients are not always positive. The gradient descent also generally performs well where the input features are centered around 0 and they have comparable variances. Essentially, whenever we are using either the weights or the input X, they should always be within proportion to each other. At least the weights should be in proportion to different weights and the input also. Now any standard neural network initialization or activation functions assume a standardized input. Let's take a quick example for this. So there are different initialization like Xavier and Glorot which assume the input variance to be 1. Let's assume that we have an input layer. So let's assume my y is given as summation from 1 to m wm xm, which could be written as w1 x1 plus w2 x2 and so on, which is given as y. Now if we take the variance of y, it is essentially variance of w1 x1 plus variance of w2 x2 and so on, which would essentially mean, since my variance of different weights, the variance of w1 x1 is the same as variance of w2 x2, hence let us take the summation as n, then the variance of y is represented as n times the variance of w1 times x1. Now this can further be broken down into variance of y is given as n times variance of w times variance of x. Let us assume that the variance of w is 1 by n. If that happens, then the output variance becomes something closer to 1. So the input variance was 1 and the output variance is close to 1. Hence these are distributions or which are similar in scale. My input was similar to my output, right? The variance is comparable, even if it's 1.5 it's okay because it is comparable. However, let's assume a case where that is not true. Let's assume then the input variance is very high. If the input variance is very high, the output variance would also be very high. If the output variance is also very high, during back propagation the gradients would have a very high number during an update, and hence the gradients would explode, right. So although they, now let's quickly also go over a phenomena known as the covariant shift. Covariant shift occurs when the distribution of each layer, while the learning algorithm is going on, the distribution of each layer keeps changing, right. Since the distribution keeps changing, it becomes harder for one layer to keep adapting. So let's assume my x is my input layer, y is my output layer, h1 is the hidden layer closer to the input and h2 is the layer closer to the output, right. Now let's assume I am looking at h1's weights to be updated. So I am looking at these weights to be updated, right. Let's look at the first neuron, right, and we would have connecting weights. Now each of these weights depend on each of these neurons, and each of these neurons have a changing distribution. So for the first iteration it's this, for the second iteration it could be vastly different, right. Now if that is the case, then the distribution of the layer, hidden layer h2 keeps changing, which means there is a very drastic change of w1, right, and hence it becomes harder for h1 to keep changing because h2 is keep changing. It is harder to learn when h2 is more dynamic. It will keep evolving, hence the weights will keep evolving, hence the delta w update that we get will keep changing because the local gradients will keep changing. This is something that we term as the internal covariant shift. It is internal because there is no outside influence. It is internal because the weights which are the previous weights have an issue because the weights near to the output keep on changing its activation function during the learning algorithm. Now this is something that we try to address using normalization. There are some hypotheses that suggest that normalization is helpful for this particular criteria. There are some contrary views. However, normalization techniques in general are much better while we are training the multilayer perceptron or even the CNNs. So let's maybe take a deeper look into different normalization techniques. But again, just to discuss the effects of internal covariant shift. Internal covariant shifts generally cause a slower training. So the model does spend a lot of time adapting to the distribution changes rather than learning useful features, and this is adapting to the distribution changes in its own model itself. So H1 actually has an issue with learning weights from H2. It does require lower learning rates. This is essentially to prevent instability. We also need to carefully initialize the parameters. They could not be vastly different, right? Our network suffering from internal covariant shift is now more sensitive to scale initialization. And lastly, we would also explore something known as vanishing and exploding gradients. This is essentially because a shifting distribution could amplify existing problems of vanishing and exploding gradients. Okay, now let's take a look at normalization of a feature map. So let's define a very basic normalization operation and let's then go over different types of normalization. Okay, now let's consider a feature map X at any layer. So I have an input, we have the input, we pass it through a CNN backbone. Now when you pass it, let's take the feature map at any layer of that particular backbone. It could be an output of the CNN, it could be output of an MLP. It is just an output of any neural operator, which is either a convolutional operator, max pooling operator, activation function at any stage. Let's take that as a X, which is the feature map. Let's try to make it as a zero mean unit variance. Zero mean means the mean is 0, variance is 1. This is represented by this equation. So x cap of k is given as x, which is the feature map, minus the expectation of x divided by the square root of the variant of x, right. So essentially we have a feature map, we are subtracting it from the mean of that feature map, dividing it by the square root of the variance of the feature map. K is, it could be kth layer, it could be kth minus 1 layer. So essentially it could be any layer, we are interested in the feature map per se. This operation is a differentiable operation. So this could be put in part of either a MLP or a CNN backbone, and hence it is differentiable. Okay. Now normalizing the feature map leads to a more stable and consistent activation across the layers. Now why is that? And before we proceed, let's give this activation name as Z normalization, right. So let's call it like a Z normalization block. Now what are the effects of normalizing a feature map? Now let's assume we have the orange curve, which is the actual feature map. So it is the actual X, and let's identify the blue one, which is given as X cap. Let's make it capital. Now X cap is essentially after the normalization process, which means its mean is 0 and its standard deviation is 1, right. So one way to look at it is, it has been shifted to have a different mean. Earlier the mean was somewhere here, which is close to 4. Now the mean has become 0 and we want the mean to be 0, right. So normalization, essentially the effect is, it centers the distribution around 0 and it reduces the variance to 1. We can observe that the variance of this particular orange curve is pretty high. You can see it is very well spread, whereas the blue curve, which is the same curve but just normalized, the spread is much lesser. Okay. Now this is an effect of one feature map. Let's take different types of feature maps, right. Now if I take Z score normalization, which is just a name for the previous normalization, it is essentially a linear scaling, which is it shifts and stretches the value, but the shape is preserved. So we do not influence what the feature map is trying to represent, we just try to shift it so that it is consistently across a certain mean and standard deviation. So let's assume we take feature map 1, which had a different mu and sigma. After the normalization, it does have comparable mu and sigma, similar, but its shape is preserved, there is no influence in the shape. Let's for example take feature map 3, which is using which is with a particular mu and sigma. After the normalization, we actually observe that the shape is retained, and this is essentially for most of the curves. So normalization is more of a shifting operation, but the shape is not influenced. Okay. Now before we go into different types of normalization and its effects, let's maybe quickly go over some basic definitions of terms for training. Let's start with batch size. Batch size is essentially a subset of training dataset which is processed together in a single iteration. Essentially, the batch size determines how many samples is fed to the model in one go before updating the before computing the gradients. So essentially, if I take an example of dataset D which starts from x1 comma d1, apologies for this, x2 comma d2, x100 comma d100. Now if I take the batch size as 10, it is essentially choosing 10 samples of, it depends on if it's randomly or not, let's keep it as random now. So batch size is 10, right, which means from this whole data set I can take 10 samples and I can pass it on to the model. Once we pass it on to the model, before computing the gradients. Now this is also something we saw last time. This is something similar to the batch learning where we selected n samples and then we passed it and then we computed the average of the gradients. Okay, now we know what is batch size. Batch size is essentially I take 10 samples or n samples, I pass it to the model and I compute the average gradient of error. Once we have batch size or batch, we define the iteration. Iteration is essentially a single forward and backward pass, which is we have passed it on to the model and we have updated on one batch of data. So essentially if my batch size is 10 for one iteration, right? After each iteration the model's weights are updated. And lastly, a complete pass through the whole data set is essentially defined as an epoch. So let's assume I have this batch size and I pass it for one iteration. Now I have to keep doing it again and again so that my samples which started from 10 actually go over the whole data set. So it actually passes through 100 samples, the entire training set. Once I pass in through those iterations, I would get one epoch. So one epoch is essentially the total number of samples divided by the batch size, right? So in this particular example, if I had 100 samples and if my batch size was 10, essentially my epoch is 10 iterations, right? So that is one, these are some of the main terms which we use during training. Now any feature map that we have, we can represent it in this particular format, which is B is the batch size, C is the channel, H is the height, W is the width. So essentially we have the number of channels which are defined as C. We have the resolution of this feature map which is defined as W, and batch size is essentially what we defined earlier. It is the batch of samples that is passed to the model, right? So B is the number of samples in one batch, C is essentially the depth, and height and width is essentially the spatial height and width, right? This is something, height and width is something we would have seen, even the channels is something we would have seen even in the CNN lecture. The batch is essentially what we define when we are passing it to the model for each iteration. Now let's go over various normalization techniques. Now during training, let's assume I have a layer X. Batch normalization is defined as first computing the mean, which is given as mu, which is essentially just taking the mean for all the channels. Now we have the variance that we compute. So the variance is given as sigma j square, which is essentially 1 by n I from 1 to n, x minus mu whole square for various elements. Once we have this, we will essentially try to normalize. So x is given as x minus mu upon sigma square plus epsilon under root. Epsilon is there for numerical stability. So in case my sigma square is very small, right, then it may cause some issues, like x would be very high. So we want to maintain the scale, so we add a epsilon so that it maintains the it doesn't let it become unstable. It doesn't, so the denominator is not made 0, it's there for just that, for numerical stability. Okay, now the equation we see at the bottom, which is x cap, is similar to the z normalization. However, mu and sigma is something that we compute using the above equations. Now once we have done that, we use an affine transformation. Affine transformation is I have x cap, I pass it through gamma and beta. So the output y after the whole normalization process is given as gamma times x cap plus beta. Again, gamma and beta are learnable parameters. Now main advantages of batch normalization are the networks become more robust and there is zero overhead at test time, right, because all these terms which are required are computed during training, it is not during test time. So all the learnable parameters mu and gamma are frozen. However, one major drawback of this is the mu and sigma which are computed during training. Once they are computed during training, they are kept frozen during testing, right. Now an issue with this is if I have a train set which is dt and I have a test set which is dtest. Now I have computed mu and sigma for various layers in the whole model, right, due to batch normalization. The same thing has to be used here because it is frozen, it does not get updated. But if the distribution of both of these sets is very high, then this is not good. This is a common source of bugs or a common source why models do not generalize to extremely different test set, because mu and sigma are something which are sampled out during the train set. Okay. Now during inference is something that we saw. The estimates depend upon the mini batch, which is essentially the average of values during training. The learnable parameters are kept frozen, right, and hence this may cause an issue because once these averages are computed during training, during testing they are just used as it is without any updates, and if there is a drastic change it will cause an issue. During training, batch norm essentially acts as a numerical linear operator because it has linear terms which are frozen and these terms are essentially just taken from the train set. Okay, let us look at layer normalization. Now layer normalization also follows a similar pattern. So we calculate the mean, we calculate the variance, let us not call it as channel, let us just say it is mean and variance. Once we calculate the mean and variance, we normalize the feature map. So x cap is the normalization of the feature map. Now we calculate all of this along the batch axis. So let us just write how a feature map is represented now. The feature map would be represented by batch size, comma channel, comma height width. Now I also represent, so essentially I represent n and b as similar. So when I say n, it also just means b. So we are essentially taking normalization across the batch axis. So mu is taken in a sense which is across the batch axis. So it is taken mu only of these remaining axis which is channel, height, width. Similarly for sigma, right, and then we perform an affine transformation which is y I is given as gamma times xi cap plus beta, right. Now layer normalization is applied to one observation at a time and it is a deterministic transformation that standardizes the activations at a given scale. The important part to remember is that although the operations are similar, they are different across different axes. So layer normalization is across the batch axis. Now let us take a look at a different type of normalization. This is the instance normalization. In instance normalization, the mean is computed in a similar manner which is mu, the variance is computed in a similar manner which is sigma I, and we calculate the normalized feature map which is given by this equation. So the process remains the same. The important part is across which axis are we taking the mean and variance. Now for instance normalization, this is across the N and C axis. So if I again write my feature map in this particular equation, which is batch size, channel height, width, and again the batch axis is given as B. We already have defined that B and N are similar. There is no difference between B and N. Please do not get confused. Now the instance normalization is across the batch and channel axis. When I say it's across, it is essentially only taking the mean and variance across the height width feature map. It is across the height width of the feature map. Now instance normalization computes mu and sigma along the height width for each sample and each channel, right. Now once we have calculated x cap, which is the normalized feature map, we pass it again to the affine transformation and we get yi, which is gamma times xi plus b, and whatever were true for batch normalization is true here also. The mean and standard deviation are calculated during training and they are kept frozen during inference. Okay. Lastly, let us take a look at group norm. So group normalization is given by, we calculate mu, which is the mean across the feature map. We calculate the standard deviation. Once we have this, we normalize the feature map x cap, which is given as xi minus mu I divided by sigma I. Now one important part about group normalization is, although it is across the batch axis, it works a little differently compared to say layer normalization. Now we define a term which is C by G, which is the number of channels per groups, right, and this is highlights the lower floor operation. Essentially group normalization computes mu and sigma along the height width axis and along a group of channels only. It is not across all channels but across a selected set of channels, which is highlighted by this equation. Affine transformation is given as y is equals to gamma times x plus beta, right. Now although this may be a little bit confusing, let us maybe look at a example that would clear a lot of these doubts. Let us look at a summary of different normalization. Now let us plot batch size, channel height, width, right, and when I say batch size, it does mean it is equal to n. So it is just a notation. Now if we look at the batch norm and if I look at the axis here, it is across the channel axis. It is across the channel axis. If we look at layer norm, it is across the batch axis. If we look at instance norm, it is essentially across both channel and batch axis. So it's like only at the height width at each element, right. And if we look at group norm, it is essentially across the batch axis, but you see it is only to a selected set of channels. It is not for all channels. Now if we take group normalization actually becomes layer normalization if G is equal to 1, right. So if I operate it across all the channels, then it is similar to layer normalization, and group normalization becomes instance normalization if the groups is kept where G is equals to C. Okay. So this is essentially a way to visualize the feature maps, and this is essentially a way to relate batch size, channel height, weight, which is a 4D representation of a tensor, to a 4D representation pictorially. Okay. Now let us also take a different look into what it means when we talk about information in an image. If we look at an image here, we can see that there is the car, and the car would have particular features, right. It would have shape, it would have the texture, it would have certain semantic information. Now when we look at the content information is generally the spatial information. This is highlighted either by edges, shapes or lines, right, and this is generally observed during the activations across height width. So I do not need any other information. If I look at this in this particular height width feature map, I can observe that there are edges, shapes and lines, right, and this gives me meaningful content information about the car. Let's look at the style information. The style information is generally retained in the channel statistics. So it is either across mu or sigma, and this highlights the texture of an image. And maybe let's take a different look into what does it mean as the texture of an image. However, just to conclude, the spatial pattern is completely different, right? But two images have the same per channel mu and sigma. They may stylistically look similar, right? Now, what can we take a deeper look into what does it mean by style or texture? So, if I take an RGB image which is highlighted by this car here, we have style information from a different image, and if we try to merge both of them, right, which is content plus style information. So I have content from the RGB image, I have style from the middle image. I can see that the overall mixture of content and style, how does it look like? So this is what we define as the texture of an image. You can see there are certain styles which are here in this image which are reflected even here, right? These are the texture which are reciprocated or transferred, right? So just to conclude, we have a content image, we take style from a style image and we try to impose the style on the RGB image. Once we do that, we get an image which has content and style both, but the style comes from the style information. Now the style captures the texture, whereas the content captures the structure, right? And although this is true for an image, because we are essentially understanding how the image works on, this is also true for the CNN feature maps. So each layer in the CNN would actually learn specific information. However, it would have content and it would have style, right? And an intuitive way to understand this is the CNN is essentially used to understand the information in an image. So it should by default try to focus more on understanding the content and style of the image. Now let's take a different example. Let's take RGB image which is highlighted here. Let's try to do a different activity, right? Let's just take the mu 0 and sigma 0, which is the channel statistics of RGB image, and try to update it with the mu and sigma highlighted here, right? That mu and sigma is essentially something that we take and we add it here. So the cool cinema actually has the content of the RGB image and it has the style depending on the channel characteristic that we have given, right? We can observe that the texture of this image has changed. Similarly, we can do the same for a different setup as well. We can have different mu and sigma and we can add it to the original RGB image and we can see that the texture of the image changes. Now it's very hard to quantify the texture and content because it is overlapped in an image, but this is just to give you an idea what it means when we say texture. Now we can use this particular equation, which is the adaptive instance equation, to attain either the cool cinematic or the golden hour view. We take and modify this image to get this particular cool cinematic image. So we take a feature map, we normalize the feature map, and then we add sigma 1y and mu 1y, which is given as these default values, and update the feature map, and this is how we get the cool cinematic views, right? Similarly for the golden hour. Now one particular part that we wanted to say was, we can do this in the image space because an image has content and style information. We can also do it at a feature level space. So we have a feature map X. The feature map would have content information. So what we could do is we could essentially just normalize this and focus more on the content part of it, which is C, and we can add style from a different source, or we could just manually tune the styles as we have done here and update the same image. and you would observe that the content is preserved but the style is modified. Now let's take a quick look into adaptive instance norm. Again, we will take a deeper look into adaptive instance norm in generative AI module. However, let's quickly go over what is the operation. Adaptive instance norm essentially is used to transfer the style. It injects the style statistics into the features which would have content, right? So this is similar to how we saw. We would try to normalize the feature map and try to add the important style, which is similar to this equation as we see in the bottom. Okay, adaptive instance, which is ADA-in, enables fast neural style transfer, which is essentially a style transfer mechanism. The content image provides the spatial structure, which we can see from the activation here. The style is essentially the channel wise statistics which we embed in this equation here, right? The style transfers happen in a single forward pass without an iterative mechanism, right? And hence we have an adaptive instance norm. So formally to define an adaptive instance, which is given by x and y, which is sigma of y times the normalized version of x plus mu of y. Essentially we get the content information from x, which is highlighted in this activation, and we get the style information from y, which is why we are borrowing the style information from the channel statistics of y. In the previous example, we manually gave or defined sigma and mu. However, we can actually take the style from a different source and inject it into the model. So a very brief overview of adaptive instances. We have this, which is x, which is the content image. We take style from y, which is the figure below, and we try to inject it in the feature map itself using the above equation, right? Once we do that, we try to reconstruct this information. Now please don't go in detail about the decoder part. I know it has not been covered, but this is just to give you a flavor of how a normalization has effect even in the texture of an image. We can see that the content image is regenerated. So I have an image which has content of x but the style of y using the adaptive instance xy, right? Okay, now let's maybe formally, we have seen the definition, we have seen the equation also. So the content image x and the style image y, essentially the equation simply aligns the channel wise statistics of x to match those of y. And an example of that is we have the figure, which is the first figure, which is essentially giving us the style information, the middle figure which gives us the content information, and we get a modified image which has the content of x and the style of y. And this is similarly highlighted even in the figure on the right, right? So these are just examples of basic style transfer techniques. However, the motivation is to understand the influence of normalization, which is not only for scale normalization, it has much wider influence. Lastly, let's take an example of normalized perturbation. Now following a very similar way of adaptive instance norm, let's take the content image x, let's take a style image y, and let's try to align the style information or the channel wise statistics of x to match that of y. Now this is the equation that we've seen before. Y is sigma times the normalized part of x plus mu. The only difference here is we have sigma s star, which is given as alpha times mu sigma c. We have mu s star, which is given as beta times mu c. Now both alpha and beta are essentially part of a normal distribution. So they are essentially just noise. They are sampled out from 0 to n, right? So in this particular normalized perturbation example, we are the channel wise statistics which are applied for the style are essentially just noisy versions of the channel wise statistics of x itself, right? And in case you want to have a deeper understanding, please go over the paper, which is highly recommended. What I am trying to motivate is, we have the content image x. Now let's just try to add noise and see its reconstruction. So when we add noise, we can see that the content of an image is still preserved However, its style is very random, and it's random because we are sampling alpha and beta from a random noise. Let's say it's from a normal distribution. We can see its influence, right? Lastly, normalized perturbation is not applied in the image space, it is applied in the backbone or the feature space. Okay. So to summarize the lecture focuses on covariant shift, which is essentially a different phenomenon that occurs while training a deep neural network. It also talks about normalization and in detail different types of normalization, which is batch normalization, layer normalization, instance normalization, etc. And it also talks about the importance of channel statistics in an image and in the feature map. So the channel statistics actually hold information about the texture of an image, and if we keep changing the texture, the style of the image keeps changing. And this is true for an image. This is also true for the feature maps that a CNN would learn. Of course, it would depend on what feature map which retains which type of content and style information and what are the effects. But this is something we will take a look in the next lecture, where we understand the visualization process. We look at what layers are actually learning what type of an information, so that in case we are performing an algorithmic development for style transfer, we know which features are having more influence in which particular part. So which features should be used for preserving the content and which features should be used to modify the style. Thank you.